register allocation is one of the most important stages in a compiler, because register allocation is the compiler stage that in which we map virtual registers into physical registers, so that our generated code is real code that can run on a real machine. And last time we presented one algorithm for doing register allocation, and the algorithm that we presented last time was a local register allocation algorithm. So what does local mean?
Within the same basic block?
Yeah, exactly, within the same basic block. So it means that the algorithm looks at one basic block at a time. So when it's allocating registers in one basic block, it doesn't know about other basic blocks. As opposed to a global register allocation algorithm, which will consider multiple basic blocks at the same time. Well, today we're not done yet with the local register allocation algorithm. So the algorithm that we studied last time is, this is the pseudocode for the algorithm. By the way, in the book, this algorithm is called the bottom-up local register allocation algorithm. So it's the bottom-up register allocation algorithm. The example that we had last time, was something like, if we look at the example, define v1. So I'm abstracting the example here with defs and uses. So again, to revisit this, what's a definition and what's a use? So if you have an operation like this, multiply R1 and R2 and put the result in R3, what does this define and what does it use?
Defines R3.
Yeah, so it defines R3. Yeah, and it uses R1 and R2. So for register allocation, we can abstract an instruction into defs and uses, what it defines and what it uses. That's what we care about. And we don't care about what actual instruction it is. Okay, so we can abstract this into define v1. This is what it does. Define v2, v3, and then there is an instruction that uses v1 and v3 and defines v4, and there is an instruction that uses v4 and v2 and it defines v5. So this is the same example that we had last time, but with the def and use abstraction, to understand, just to emphasize that from register allocation point of view, we only need to know, which registers an instruction defines and which registers it uses. Now, the local register allocator is going to look at it. It's going to assume that each operation for each operation I from 1 to n, I is of the form up Rx, Ry, and write the result into Rz. So it uses Rx and Ry and defines Rz. So in this case, there is no, if it defines a register, it doesn't use anything. So in this case, the uses are absent. Here we have the uses and the defines. And for this instruction, so all what we need to do is to ensure that we have a register for each source operand and a register for the the destination operand. Okay, so we need to ensure. We will write the ensure function today. So we need to ensure Rx, and we need to ensure Ry, and we need to then rewrite op as op px py goes to pz, where px is the result of this and py is the result of this, and pz is the result of the allocate. Well, let's move this. So pz is the result of allocate of rz. Then rewrite op as op px py into pz. Okay, so ensure, find a physical register for this, and find a physical register for this. Then for the destination, we always need to find a physical register. So that's why we go straight to the alloc. Now ensure, what do you think ensure should be doing? Ensure of register R. What should it do based on what we did last time? So for this, ensure is going to get called here for V1 and V3. What will it do?
Check the free list or a free register.
No, not in the beginning. This is not the first step. The first step is not checking the free list.
If the value is already in the register,
yeah,
that's it, you're done.
Yeah, exactly. So first of all, if R is already in a physical register, then P that we are looking for is equal R dot phys reg. So now here what we are implying is that a virtual register data structure will have the physical register in it, and it will have the list of uses. This is the virtual register. And the physical register data structure, is going to have what? What do we need to track for each physical register?
Time to live, or how it's live or not?
Well, based on the algorithm that we presented last time, what do we need to track for each physical register? First, we need to track the virtual register that has it. So virtual, let's call it vreg. Okay, so this is a structure for the virtual register, and this is a structure for the physical register. So this will have the V register, and what else do we need to track for a physical register?
The next use.
Yeah, exactly, the next use. Okay, so we need to track the next use, and we need to track the virtual register. So now, in fact, R is already in a physical register. We can check on the physical register field. So these are the fields in this structure. This is the first field, the second field. So this is number 1, this is number 2, this is number 1, this is number 2. So in fact, if R is already in a physical register, maybe we can translate this into R dot physical register is not equal to some invalid indicator. And an invalid indicator, we can make it -1, for example. So -1 means no physical register. It indicates that it's not in a physical register. So if it's not -1, then there is a valid physical register, and this is what we want. Else, we need to find a physical register, to allocate a physical register. So else, P is going to come from allocate of R. Okay. And there is something missing here, so we'll have to figure it out. Return P. So there is something that we need to add in here. Let's see if we can figure it out. But for now, let's do alloc of R. So alloc is going to allocate a register, a physical register for a virtual register. So what should it do first? To allocate a physical register for a virtual register, there are 2 steps.
Check the free list.
Yeah, first check the free list. If there is one that is free, take it. If not, then try to steal a register or take a register from another virtual register. So if free list is not empty, then P equals free list dot extract. You can extract from the top of the list or from the bottom of the list. This doesn't matter. Extract top. Else, now else, if there is nothing in the free list, what should we do?
Look for the register that's used the furthest down the line.
Yeah, exactly. So the register that is used the farthest, the register, the physical register with the next. So we'll assume that we have a vector of physical registers. So let's assume that we have vector of physical registers called phys regs. So P equals I that maximizes phys regs of I dot next. So phys registers is a vector of physical registers, or call it an array. Array of physical registers that we call physical registers. So I get I that maximizes. So you have to just search for the I, search for the maximum next. Right? Get the I with the maximum next. Okay? Okay. So now, okay, so there is something that we need to add here, and then return P. So I'm leaving all of these blanks so that we'll see if we can figure out how to fill in the blanks. Right. So now let's see if we apply this. Let's apply it and see if we can fill in the blanks. So this, if we apply it to this define, it's going to go to alloc, right? So it's going to go to alloc of PZ, so it doesn't have any source operands, and it's going to go to alloc, and the free list will have 1, so it will get a physical register. So this will map V1 to P1, and similarly this is going to map V2 to P2. Why? Because the free list initially has, we're assuming that we have 2 physical registers. So assume 2 physical registers. So these will just grab P1 and P2. Now when we define V3, now we will call alloc for the third time. It will not find something in the free list. So it will get the I that maximizes the physical register dot next. And last time, this had a next of 5, I guess, and this one had a next of 5, and one had a next of 4. So a 5 and a 4. Yeah. Okay, so one had a next of 5 and one had a next of 4. So this was, V2 was the register with the maximum next. So this is the one that we need to get. Now, here in allocation, in order to give this register to V3, what do we need to do? In order to give the register to V3, yeah, exactly. So we need to spill. We need to add that, store what? Store P2 at the address of V2, the address associated with V2. So this means that here, when we get this maximum, we need to add emit store of P into the address for the physical register. So into the address of the corresponding virtual register. So in fact, with virtual register, we need another field for address. Let's say 3, the address of that virtual register. So emit a store of P into the address of this virtual register. So this is going to be P dot vreg dot address. So the virtual register that is currently in P, what's that virtual register? What's the address for that? So this is what we spill into. Okay. Now P becomes the register for this R. So what do we need to set? So either whether we allocate or we ensure. Well, here in the allocation, whether we get it from the free list or we get or we reuse, we need to set the P, right? We are giving this P to this R, right? So we need to set the P dot R, P dot V virtual register. So P dot vreg equals R. Okay, and well, in fact, this is going to be for both. P dot v register equals R, and then we return P. Okay. Now we realize that we need to issue a store when we allocate, so that we spill the register that currently has this, the virtual register that currently has this physical register. Okay. Now we will issue the store, and then this gets P2. Then we need to do ensure for these. So we call ensure for V1. When we call ensure, then ensure is going to look at the physical register, if there is a physical register. So for P1, for V1, what will happen? For V1, what will happen here? Will it be if or else? If. So because V1 is already in P1, it did not get spilled. So the register for physical register is going to be the right physical register for it has a valid physical register. Okay. Oh, in fact, here when we allocate p dot virtual register equals r, and r dot physical register equals v. So we link them both together. So we set the virtual register field for p to r, and we set the physical register field in r to physical register field in r to p. Okay. Now for the next ensure, for v3, well, v3 will also be in a physical register. So in this case, both v1 and v3 will be in physical registers. So we will not have to allocate registers for them. So v1 will be in p1 and v3 will be in p2, and here we will execute the if, not the else. Okay. But now, so we will call ensure of rx, ensure of ry, and then we will call allocate on rz. Allocate here on rz. Rz is going to be v4. So when we need to allocate a register for v4, we will look at the free list. At this point, will the free list be empty or?
It'll be empty.
No, we did not empty it, right? Because the free list here, p1 and p2 are both taken, so they are not free. So we have to free them. We have to free these. We have to free the one that will not get used later. And in this case, the one that will not get used later in the example was v3 or v1.
V3.
Yeah, it was v3. So where do we need to put the code to free this?
After the ensure.
Yeah, exactly. So here, after the ensure. Because why after the ensure but before the alloc? Because we will need it for the alloc. So the point that I'm trying to make here is that we need to free after the ensure but before the alloc. Because now here, without this, we will not find a register for this. So now we need to do if px is not needed after I, then free of px. Sorry, if rx is not needed after I, then free of px. And if ry is not needed after I, then free of py. And this free function should be easy. Free of a physical register. So what do we do with these fields at least? We set p dot virtual register to what? To something invalid, right? We are freeing it. So we set it to invalid. Let's use -1 for invalid. Or you can just say invalid here. Okay, so maybe we can just say invalid. And this is invalid. Okay, so invalid, and for next, p dot next is going to be also invalid. And in fact, would it make sense to set this to a large number or a small number? Large number, because it will not be needed, right? So we can set it to infinity. We need to set the next of this to infinity. So we realize that we need to free these before we do the alloc. Okay. Now, yes.
Can you explain what you mean by setting it to infinity? Because you want to free the
you want to free the register for the next guy. So
Mhm.
what does it mean to set it to infinity?
It means that it will not be used, basically, because it doesn't have a valid next use, because it's not allocated to any virtual register. And if it doesn't have a valid next use, then it means that it will not, as far as we can tell at this point, it will not be used.
So
Because-
why is it not okay to use invalid for that one?
Well, this is all pseudocode, so it's how you actually code it. It depends on how whether you'll be using integers or something else. But you can say invalid. That's fine. It's because this is pseudocode, and
Yeah, I just don't want to have too many
Okay.
words.
okay, so you can call this invalid next. But we want to make sure that this invalid is not -1, because -1 works here, but -1 doesn't work here, because -1 is going to be a small number, and we don't want it to be a small number. We want it to be a large number, so that when we compare it with other registers, it's not something that is used soon.
I see why you did that then. Thank you.
Okay. Okay. So yeah. So now what else? So when we ensure, and when we take a register, so we didn't get there yet. So here we defined v4, and we got a register for v4, and that register in this case is p2. v1 is still in p1. Now we need registers for v4 and v2. v4, when we ensure on v4, we will find it in a physical register already. But when we check on v2, we will not find it in a physical register. So we need to allocate for it. So yeah, so in order to allocate for it, so we find a register for it, and we will spill that. So in this case, it will get the register for which register will it get?
P1.
Yeah. So yeah, exactly. So it will get the register for P1, and this will result in spilling V1. So we will spill V1 or store P1 into the address of V1, and the store will come from here. But then, because we are we're allocating this physical register to this virtual register, what do we need to add here?
You gotta load it.
Yeah, we need to load it. Yeah, so let me move this down. So this is use v4, v2, and define v5. So this is, we need a load. Load the address of v2 into P1. And this load should come from here. So basically when you allocate, if you allocate, and this should be only under the else, right? So if it's already in a register, we don't need to issue any instruction. But if we took a register for it, so if we preempted another virtual register and took their physical register, then we need to here to do the load. Emit load from the address of this physical register from r dot address into P. Load from the address of R into P. Okay. Okay. So what is missing, in fact, here is the setting of the next for this virtual register. So P dot next. Now here we are allocating. We are allocating a physical register to a virtual register. And so we are setting p dot virtual register to this virtual register and r dot physical register to the physical register. Now the next of this physical register, what should it be? Should it be a large number or a small number? Here.
Small number.
Why small number?
Because if you get a large number, you'll end up over there to the invalid registers.
Yeah. So yeah, exactly. So it's a small number because we need it. We don't want it to be taken. So when this number is large, it will get taken. You know, the whole algorithm is based on taking the physical register that has the maximum next use. So the larger the maximum next use, the more likely it will be for this to get taken. And we don't want this to get taken because if we are allocating for two source operands, so if we are allocating for Rx, and say we give Rx a physical register that we take from some other virtual register. So we give it a physical register. Then when we allocate for Ry, we don't want Ry to take the one that we have just allocated to Rx. Okay? So if we set this to a large number, then we allocate a register for Rx. Then when we allocate a register for Ry, it may steal the register that we have just allocated to Rx. So I want to make sure that this will not get taken. So that's why we should set this to -1 to make sure that it's a small value that will mean that this will keep it. At least it will keep it until when we do this, when we allocate for Ry, Rx will still have the register. Okay? Does everyone see this point? Okay, so what is missing now? What is missing? In order for this whole thing to work, okay, no, we're talking about this logic. So, okay, okay. So we need to set the next, because when we move past one operation, the next will change. So for every virtual register, so if this is operation I, when we are done with operation I, so the next for this V1, it's currently I. But if V1 is used later, then we need to update the next of V1 to the next use of V1. So for every virtual register, if Rx is used after I, update px.next. If Ry is used after I, then update py.next. And pz.next, if it doesn't get used, this pz will have the result of this operation. So if it doesn't get used, the current instruction will be dead code. Right? Remember, pz is the result of the current operation, and we will assume that pz will get used. So we will not need an if statement like this, because if pz is not used, the current instruction is dead code. Okay, so we will assume that it's not dead code. So we'll just update pz dot next. Okay, so this is the algorithm. we went through an example last time, and these are the details of the details of this algorithm. Any questions on this? So it's, this algorithm is intuitive, but it's not trivial. It's not a trivial algorithm. When we look at the details, the algorithm is not trivial. It's easy, but not trivial. But we have to, understand all of these details. So the point here is that even a simple algorithm, even a simple compiler algorithm, involves some details that we have, to be aware of. So it's not that trivial. Any questions on this? Okay. Yes.
So this is for local register allocation. So in order to use this algorithm, you'd have to first pre-break all of your code into basic blocks.
Yeah, exactly. So we assume that the code has been broken into basic blocks, because a typical representation, a typical intermediate representation of the code is a control flow graph that relates the basic blocks, and within each block we have a list of instructions, list of intermediate level instructions, or it could be at different levels, intermediate or low level instructions, like the ilock that we are using in this course from the book. Yeah. Okay. So in fact, is this optimal? No, it's not optimal, because sometimes it's not clear whether we should, when we choose a register to victimize, a virtual register to victimize, to take their physical register. Right now we are taking the physical register that will have that will be used farthest in the future. But this is not always the best choice, because sometimes the best choice could be choosing a register that has not been modified since it got loaded. So if you have a register that did not get modified since it got loaded, which means it's clean, right? Or since it got defined the last time, if it did not get modified since the last load, that's a clean register, which means that you will not have to store it in memory. So you will not need a store. So choosing a clean register for spilling will save us a store operation. So if it's, if there is a load and then loading this register into P1 and then it does not get modified and we store it again. So this store is a store that we can later identify as useless code, and we can eliminate the store because it did. So this, as we said, last time. So which happens here. We are storing this after defining it, or it was a load in the example. So a store is not needed for a clean register, and by doing this, you save yourself a store operation. But in general, it's not clear whether the right choice is to select a clean register for spilling so that you avoid the store, or you choose the register that has the farthest use in the future. Because if you don't use the register that has the farthest use in the future, or in other words, if you keep the register that will be used sooner in the future, then you may get lots of good hits, and you will not have to do a lot of allocation and replacement. So if there is a register that gets used many times in the future, in the near future, you better keep it in a physical register, because you will keep using it over and over and over. So it's not always clear what the right decision is.
Now I have a question about that. If you load P1 and then you don't use it, and and you need it for something else, why do that load in the first place?
Well, go back to the example that we did. It's used later, somewhere later, but this store was not in the original code.
Right.
This store is a spill that got added by our register allocation algorithm. So our register allocation algorithm added this store, but some of the stores that get added, if they get added immediately after the load, or if they get added before we ever use this is a useless store and can get eliminated later. Okay, so this was not in the original code. This is something that our algorithm added. So the point that I'm trying to make is that it's not always clear what the right decision is. Whether you should spill a clean register so that you avoid storing it in memory, or you should spill the register that will be used farthest in the future, because spilling the register that will be used farthest in the future is equivalent to keeping the register that will be used soon in the future, that will be used in the next instructions, and that register that will be used next may be used multiple times, and then by keeping it in a physical register you will get lots of hits. You will not have to load it over and over, so it will be in a physical register, and it's not always clear. That's why it's not always clear which decision is the right decision. Okay, so this ends our discussion of local register allocation. Any questions?